Welcome to the UML Design Class Diagram Notation crash course. In this video we will look at the detailed notation for creating class diagrams and how these translate into an implementation. The basic notation for a class is a box as usual. It can have three compartments, one for the class name, one for attributes, and one for the operations of the class. There are some special notations you can use for the private attributes, protected attributes, public attributes, and also package protected attributes. It is not certain that every implementation language supports package protection. And you can have the same notation for operations also, public, protected, or private. You can initialize values using this notation, and maybe more importantly, you can see the type of an attribute by using this notation. You can have arguments to operations and of course return values with the type. A special and a little bit tricky notation is for abstract classes, and then you write the class name in italics. This is not always easy to see, and also the abstract operations are written in italics. So that is something to look out for when you look at class diagrams. You can have interfaces, and this also displays one important thing about UML, that it can be extended using stereotypes. So you add the stereotype interface to a class, and then it's interpreted as an interface with special restrictions to it. There is also an alternative notation for interfaces in UML, and this is this circular notation or lollipop notation. We will see how this is used later when we talk about the relations also. In addition, you can have another type of special class, an enumeration class, and then you stereotype it with enumeration, and you can put the enumeration values into the compartment. Finally, a little bit more advanced, you can also have template classes where you define a template parameter. This is typically used for collection classes and generics in Java, and so on and so forth. Finally, we can put everything inside a package, and this is quite a common notation for this. The relationships between classes and interfaces are of much more interest when we are doing design. Basically, there are four types of relations we can have between classes and interfaces. The most generic one is the dependency. A little bit more specialized is the association. We have also the generalization specialization relation and the realization relation. We have two special types of association that we are going to talk about also, the aggregation and the composition. The generalization specialization relation is simply implemented by inheritance in object-oriented programming languages. Often this is shown as a special keyword. In this case, we can see that the class generalization specialization extends the dependency superclass. And this means that we have this type of notation in our UML diagram. Realization is implemented by interface fulfillment. Often this also has a special keyword in an object-oriented programming language. In Java, it's implements. So in this case, realization implements an interface and another interface. The UML notation for this looks like this. Please note that there are two different ways of showing interface realization. You have the normal notation and you have the lollipop notation. The lollipop notation is more common in component diagrams, but sometimes you also see it in class diagrams. But it means exactly the same thing. Associations are implemented by using an attribute. In this case, the association class contains an attribute of type association target. This attribute should have the name role name, and it should be able to contain many instances of association target objects. This is often implemented using some form of collection class. In this case, we have selected to use an array list that contains association target objects. The attribute name is role name, and this is how this relationship is implemented. Vice versa, if you see an attribute of a certain type in a class, then you have an association. You do not add these attributes in the attribute compartment of the class. Instead, we want to show the relationship visually. Aggregation and composition are special types of associations. They are both implemented as associations, and there is no real way to look at an implementation and directly see if it's an aggregation or composition. This means that if you do reverse engineering, you will always end up with associations. And in general, do not spend too much time deciding on aggregation or composition. Use association instead. Composition indicates object ownership, and this could be important in certain circumstances. So this indicates that when the whole object is created, the part objects should also be created. And vice versa, when the whole object is deleted, the part object should also be deleted. And part objects are not shared between different whole objects. This means that if you copy a whole object, you need to copy also the part objects. This means that you need to do a deep copy. The indication of composition is useful in non-garbage collected languages where you need to manage your own memory, or if you have a special application where you yourself try to manage memory, for example for performance reasons. Aggregation semantics are not well defined. This means that the aggregation is interpreted differently by every developer, and thus you should avoid using aggregation altogether. There is no real difference between aggregation and the common association. A possible reason for having these three types of associations is that, for example, in C++ we can have different types of memory management for attributes. You can have by value, and this would indicate the composition. You can have by reference, and this would indicate aggregation. And you can have pointers, and this would indicate association. But if you use a modern language with garbage collection, you should always go for the common association, as this is actually what you most often will need. Finally, we have the dependency relation. And this is basically everything else. So if you don't have any of the more special types of relationships, then you should use the dependency. And basically this boils down to local variables in operations. You may be called constructors, you can have arguments to an operation, or you can have a return type from an operation. And all of these would indicate that you need to use the dependency. Finally, you can also have global access to an object or use static operations. This is of course in general bad practice and should be avoided. The dependency is considered the weakest type of relation. So we do not add dependencies if you have another more strong relation to the target class. So for example, if we already have an association, then we do not add additional dependencies between the same types. We also do not add a dependency if we have a relation in a parent class or an implemented interface. We can also have inner classes, and basically this is the same notation as for packages, and the more specialized notations here can also be used to show class containment in a package. The easiest way to show inner classes is to simply put the class inside the outer class. We can also show that the inner class is a part of the outer class by using the UML anchor notation. And finally, we can use the qualified name. In this case, we use a double semicolon to indicate the outer class, and you can also use packages for this notation. This is especially useful if we have a tool that do not support any of the other notations to show package containment or inner classes. We have some special rules for dependencies between packages. So in the first case, if all classes in the first package depend on one class in the second package, then we can simplify this so that the package 1 depends on class number 4 in this case. We can also note that if all classes in package 1 depend on all classes in package 2, we can say that package 1 fully depends on package 2. This notation is not interpreted as this in all cases. So when you use this type of notation, you need to make sure that everyone interprets this correctly. In this course, these are the rules that we will use.